SwayamPrabha. Digital India. Educated India.
Good morning everybody. Today we will discuss about the diffusion equation and the boundary conditions. Now for some applications we are required to deal with the problems in which the temperature of a solid body may vary with time and in more than one direction. Such heat conduction problems can be tackled by solving appropriate differential equations based on the first law of thermodynamics. In deriving the differential equation of heat conduction, we shall assume that the material of the solid is isotropic. However, the conductivity may vary from point to point in the material if the property is temperature dependent. We will consider an element dx, dy, dz located arbitrarily within a solid material. We will assume that there is heat generation in the material too. Now, in the given body, as we mentioned earlier, we can see we have taken an arbitrary element dx, dy, dz, and let us take a point P at the geometric center of this element dx, dy, dz, and let qx double prime, qy double prime and qz double prime be the x, y and z components respectively of the heat flux vector at a point P. The resultant heat flux vector is basically q double prime, and the x components are qx double prime, y component qy double prime and z component qz double prime. Now, by making use of Taylor series expansion, the heat flux components on 6 surfaces. So this q double prime, which has components qx double prime, qy double prime, qz double prime at point P. Now we will make the Taylor series expansion of this heat flux components on 6 confining surfaces. Now this is at the center. The x component of heat flux is qx here. Now at a distance minus delta x by 2, we consider heat flux on this left surface qx1 double prime, which is given by Taylor series expansion. If we follow q double prime x minus delta x by 2, so it will be then qx double prime minus delta x by 2 del x of qx double prime plus delta x square by factorial 2 into 4 del 2 del x2 qx double prime. Now on the right surface, which is at a distance plus delta x by 2, we consider qx2 double prime, which is given by qx double prime, again through Taylor series, delta x by 2 del x of qx double prime, delta x by 2 square by factorial 2, that means delta x square by 4, and in the denominator factorial 2 del 2 x double prime del x2. So this is on the right surface or the right face. Now similar way, qy1 double prime, which is on the basically front surface and which is delta y by 2 behind the point P, it is q double prime y minus delta y by 2, and that is again qy double prime minus delta y by 2 into del y of qy double prime plus again delta y by 2 square divided by factorial 2 del 2 del x2 q y double prime. So this here we can see minus sign for the Taylor series expansion, the point which is behind the point of interest. Here also we can see minus sign. Here we can see plus sign because it is on the right face. Similarly on the face, which is the back surface, we can write qy2 double prime equal to q double prime y plus delta y by 2. This is, delta y by 2 ahead of the location of the point P. So delta y double prime qy double prime plus delta y by 2 del y of qy double prime plus delta y by 2 square divided by factorial 2 into del 2 del y2 of qy double prime, and this is plus. So this is minus, this is plus, this is minus, this is plus. Here all the components, the second derivative, are having positive sign. Now in a similar way we have done up to the heat flux at the back surface. Just for smooth continuity, we have repeated the expressions for qy1 double prime and qy2 double prime. Now at the bottom surface, this is qz1 double prime. This is given by q double prime z minus delta z by 2. So this is delta z by 2 below the location of point P. So that is why qz double prime minus delta z by 2 del x of qz double prime plus delta z by 2 square divided by factorial 2 del 2 qz double prime del z2. Similarly, qz2 double prime, that is the heat flux at the top surface, q double prime z plus delta z by 2 equal to qz double prime plus delta z by 2 into del x of qz double prime plus delta z by 2 squared divided by factorial 2 into del 2 qz double prime del Z2 at point P. Here again we can see that the first derivatives will have alternate negative and positive signs, and the second derivatives are having, the expressions are all having positive sign. So now we can calculate decrease of energy of the element due to the net outward flux in x direction, and that will be clearly, if we look at it, qx2 double prime minus qx1 double prime, and then we can write basically del x of qx double prime at point P into delta x plus del 3 del x3 qx double prime 2 del x cube divided by factorial 3 into 2 cube. So plus and this is the heat flux into the area, so total energy delta y into delta z. So this surface is delta z into delta y into delta z. So this entire surface, left surface and right surface, will come into play, and delta y into delta z. Dz, dy dz, we are writing delta y into delta z plus higher order terms. Similarly, net outward flux in y direction, so that will be then again q y2 double prime, that is the heat flux at the back surface into the total area, minus qy1 double prime at the front surface into total area, and this area is delta x into delta z. Dx dz we have written, and instead the quantity, I mean the magnitude wise, we can say delta x and delta z. So we can write del y of qy double prime at point P into delta y plus del y3 of qy double prime into twice delta y by 2 cube by factorial 3 into delta x into delta z plus higher order terms. So this way we can calculate, in z direction also. The time rate of change of, so this is basically energy that is leaving the element, dx dy into dz, or delta x delta y into delta z, that element, the energy that is coming in and going out, we are calculating a flux. Now time rate of change of internal energy of the element can be expressed in terms of the average temperature of the volume element, that is rho Cp into delta x into delta y into delta z. So this is the volume into rho mass into Cp into del T, this is temperature, average temperature, del time. This is basically the time rate of change of internal energy. And the rate of increase of internal energy due to heat sources, if Q average star is the volumetric heat source, then Q average star into delta x into delta y into delta z. Now we can apply first law of thermodynamics, that is basically time rate of change of internal energy equal to a flux of energy from the surfaces. This is a first order term, this is a second order, higher order term. So these two terms, basically a flux of energy from the confining surfaces, and this is the energy generation rate based on the volumetric heat source. So now from here we can write basically this rho Cp del T average del T, and a special mention had to be done that the minus sign has been used to indicate the energy leaving the system. So further simplification, we can say rho Cp del T average del time equal to minus del x of qx double prime within bracket del y of qy double prime and del z of qz double prime plus q average, q star average. What we are doing, basically we are cancelling out this del x, del y, del z, that means the volume, elemental volume, that gets cancelled out from all the expressions, the time rate of change of internal energy, a flux of energy and generation of energy. Everywhere the volume is given by this quantity del x, del y, del z, and we can sort of cancel out that, and we can write rho Cp del T of T average equal to minus gradient of fluxes in respective directions plus Q average star minus 2 divided by factorial 3 into 2 cube. Here del 3 qx double prime del x3 into delta x square plus del 3 qy double prime divided by del y3 into delta x square and del 3 del qz double prime del z3 into delta z square. This should be del 3. This is del 3 del z3 qz double prime. Please read as like this is a third derivative del 3 del z3 qz double prime into delta z square. Now in the limit of delta x, delta y, delta z tend to 0, all dimensions tend to 0, that means the volume is shrinking at a point, and these higher order terms will be shrinking faster because these are del x square, del y square, del z square. So this term will disappear, and T average will be Tp if it shrinks at a point. Q star average will be Qp average, and higher order terms will tend to 0. The final result will be rho Cp del T of Tp equal to minus grad dot Qp double prime plus Q star at point P. Since P is any arbitrary point because this cube was any arbitrary cube. So when this cube shrinks to a point, so P is any arbitrary point, the equation is valid at any point in the body. So we can write rho Cp del T, this T is temperature, del time equal to minus grad dot Q double prime plus Q star, where Q double prime is basically, this is resultant heat flux vector. It has three components, I Qx double prime plus J Qy double prime plus K Qz double prime, and the quantity Q star is give and Q double prime is given by, we have seen in earlier lecture that this heat flux is given by minus K thermal conductivity into grad of T, temperature gradient. So let me repeat that Q double prime can be written as I Qx double prime plus J Qy double prime plus K Qz double prime, and also Q double prime, this is the components of heat flux vectors in three mutually components of the heat flux vector in three mutually perpendicular directions, and the heat flux vector Q double prime is otherwise given by K into grad T. This we have seen earlier, that this is minus thermal conductivity into temperature gradient. Now we can write rho Cp del T del time equal to grad operator dot K grad T plus Q star. This Q star is rate of generation, volumetric heat generation rate. Rho Cp del T del time equal to grad dot or nabla operator dot product of K grad T. Now if we simplify this or work out this, we will get del x of K del x of T. So del x of K del T del x plus del y of K del T del y plus del z of K del T del z plus Q star, this is the volumetric heat generation rate, equal to rho Cp del T del time, del temperature del time. If the thermal conductivity is not a function of space, if it is constant for the isotropic material, then we can write del 2T del x2 plus del 2T del y2 plus del 2T del z2 equal to Q star by K equal to plus Q star by K, del 2T del x2 plus del 2T del y2 plus del 2T del z2 plus Q star by K equal to 1 by alpha del T del time. And this alpha is basically after dividing this by K, so this is becoming 1 by alpha. So K by rho Cp is alpha. So when K is coming to the right hand side, it is becoming 1 by alpha. Alpha is K by rho Cp, and this is thermal diffusivity. So alpha is the thermal diffusivity, K by rho Cp, and if we want to understand its implication, then this is thermal conductivity of the medium divided by rho Cp is nothing but thermal capacity. So a large value of alpha implies that a medium is more effective in transferring energy by conduction than it is in storing energy. Now, under the steady state condition, this temporal term can be dropped. We can write del 2t del x2 plus del 2t del y2 plus del 2t del z2 plus q star by k equal to 0. This is Poisson's equation for temperature. Now, in a similar way, what we derived in the earlier topic is basically heat conduction equation, governing equation. Depending on the situation, we can apply for unsteady state flows or unsteady state condition, unsteady state heat conduction, we can apply this equation, and steady state heat conduction, we can apply this equation, Poisson's equation. So it is, and basically this is the governing equation for heat conduction. And then we can derive that in cylindrical polar coordinate system, basically r, theta, z with the cylindrical polar coordinate system. We can see that the final expression, this is rho Cp, again del temperature del T plus 1 by R, del R of Rk del T del R plus 1 by R square, del theta of K del T del theta. Theta is the direction of the angular variation, and this is del Z of K del T del Z plus Q star. So further simplification will give Laplacian T in cylindrical polar coordinate system, that is del 2T del R2 plus 1 by R del T del R plus 1 by R square del 2T del theta 2 plus del 2T del Z2. This is Laplacian T in cylindrical polar coordinate system plus Q star by K. This is the heat generation rate equal to 1 by alpha del temperature del time. And if we extend the same similar analysis for the spherical coordinate system, that is basically r phi z defined by, then we can write the governing equation as 1 by r square del r of k r square del t del r plus 1 by r square sine square theta del phi of k del t del phi plus 1 by r square sine theta del theta into k sine theta del t del theta plus q star equal to rho Cp del temperature del time. So this is in spherical coordinate system. We require to choose specific coordinate system to analyze the given geometry or a given solid, where heat conduction solution is needed to find out finally the temperature distribution over that solid body. Now, three types of boundary conditions are commonly encountered. Here the conditions are being specified at the surface x equal to 0 for a one-dimensional problem. Number one, temperature distribution may be time dependent and designated as Txt. So this is temperature function of x and time, space and time. The first condition corresponds to a situation for which the surface is at fixed constant temperature, say Ts. So we can write T0t at x equal to 0 at any time equal to Ts. So we can write here at x equal to 0, T is Ts. The second condition corresponds to the existence of a fixed or constant heat flux at the surface. So at the surface, basically a constant heat flux is maintained. So temperature variation may look like this, but minus K del T del X at x equal to 0 is Qs double prime. Heat flux is defined. The second condition corresponds to the existence of fixed or constant heat flux at the surface. We have seen that a special case of the second condition is perfectly insulated or adiabatic surface. Heat flux is 0. So del T del X at x equal to 0 is given by 0. It is basically condition for an insulated surface. The third condition corresponds to the existence of convective heating or convective cooling of the surface. That means at the surface the convective heat transfer coefficient is given, the surrounding fluid temperature is given, it may be a flowing fluid, and the temperature is also given in such a way that minus K del T del X at x equal to 0, that means heat flux here, is given by H into T infinity, the ambient temperature, minus T at x equal to 0, that means at the surface temperature at x equal to 0 at a given time. So this is called convective heating or cooling condition. This is the third condition, and little more extension of this condition is also to include where the surface temperature, despite getting cooled by the ambient fluid, is quite high. There also we can get the contribution to radiation. So you can see, because of this temperature gradient, Q double prime conduction, that means conduction heat flux, is defined at the surface, which is basically equal to the radiative heat flux and the convective heat flux. So Q conduction double prime equal to minus Q double prime convection minus Q double prime radiation, where this is at the surface minus K del T del X, convective component is H T2, T2 is the surface temperature minus T infinity, and radiative component is sigma into epsilon into T2 to the power 4 minus T infinity to the power 4. Sigma is Stefan Boltzmann constant given by 5.7 into 10 to the power minus 8 watt per meter square Kelvin, and watt per meter square Kelvin, and epsilon is basically emissivity of the surface. And usually for complex condition we use effective emissivity, and then emissivity, this is anyway less than 1, and T2 to the power 4 minus T infinity to the power 4. So temperature difference has to be very high, because we can see that to get effective contribution of radiation, because Stefan Boltzmann constant is 5.67 into 10 to the power minus 8. This multiplier one has to look carefully. So basically that what is being conducted minus K del T del X at the surface equal to HT2 minus T infinity, the convective heat removal rate, plus sigma into epsilon emissivity into Stefan Boltzmann constant into emissivity into T2 power 4 minus T infinity to the power 4. So having done this, we can easily extend this analysis for one-dimensional steady-state conduction, and there if we have a plain wall or slab which has temperature Ts1 on one side, Ts2 on other side, the slab length is L, x is the direction of heat flux given by Qx double prime. So the governing equation will be ddx of K dt dx equal to 0. So K dt dx is C1, and again integrating we get T equal to C1 by K plus C1 by K into X plus C2. At x equal to 0, T is Ts1, so C2 is Ts1. At x equal to L, T is Ts2, so Ts2 is C1 by K into L plus Ts1. So from these two relationship, we can find out C1, this constant, Ts2 minus Ts1 by L into K, or Ts2 minus Ts1 into K divided by L. And C2 we have already found out. So solution is having basically C2 and C1. So C2 is Ts1, and C1 we can find out Ts2 minus Ts1 into K, entire quantity divided by L. So Tx is basically Ts2 minus Ts1 by L into X plus Ts1. And the heat transfer rate is minus Ka dt dx. So here we can write Ka Ts1 minus Ts2 by L. And heat flux is heat transfer rate per unit area. So basically K Ts1 minus Ts2 divided by L, entire thing this entire quantity divided by A, the area through which heat flux is acting. So this divided by A, that means K Ts1 minus Ts2 into divided by L. So this is basically the heat flux. From here, a very important concept is suggested. We can say in particular there exists an analogy between diffusion of thermal energy and electrical charge, defining resistance as ratio of driving potential to corresponding transfer rate. So here if we say that if we want to apply that, that means the RT resistance to conduction, we have to write potential, that is Ts1 minus Ts2 divided by Qx double prime. So Ts1 minus Ts2 divided by or Qx double prime or Qx. I mean, if we want to keep area, we can write x. So by Qx, that means heat transfer rate. So this expression, as we can see, Ts1 minus Ts2 by Qax, heat transfer rate, this will be given by L by Ka. This will be the Ts1 minus Ts2 by Qx. This will be given by L by Ka. Ts1 minus Ts2 divided by Qx. We transfer L to left hand side, Ka to left hand side. This becomes L by Ka. L by K. Similarly, we can write electrical resistance is Es1 minus Es2 by I, potential difference, divided by the current, and this is given by L, the length of the conductor, divided by sigma into A. So where this sigma is of course electrical conductance, and for thermal circuit K is the thermal conductance, and for the electrical circuit sigma is the electrical conductance. However, a thermal resistance may also be associated with heat transfer by convection at a surface. So from Newton's law of cooling, convection we can write Q, we have used it also, H, the heat transfer coefficient, into A, the area of interest, multiplied by Ts minus T infinity. So resistance, here we earlier we wrote resistance to conductance or conduction resistance. Here the convection resistance is given by Ts minus T infinity divided by Q. Same concept, the potential divided by the transfer rate. So potential, driving potential is Ts minus T infinity and the transfer rate is Q. So the resistance is 1 by HA. This is yet another example. Ambient temperature is T infinity 1. This is a solid surface. Temperature is Ts1 and thermal energy is conducted. Here the temperature is Ts2, and for this particular case, on the right hand side of the slab, again we have local ambience where temperature is T infinity 2. So what we can do, we can set up electrical circuit equivalent between T infinity 1 and Ts1. The resistance is 1 by H1A. Between Ts1 and Ts2, resistance is L. This slab width is given by L divided by Ka, and between Ts2 and T infinity 2, the resistance is 1 by H2A. So this resistance is 1 by H1A, this resistance is L by Ka, thermal conductivity, and this resistance is 1 by H2A. H2 is the film heat transfer coefficient of this surface. The equivalent thermal circuit for the plane wall with convective surface conditions is shown here. The heat transfer rate may be determined from separate consideration of each element in the network. So Qx can be written by T infinity 1 minus Ts1 divided by 1 by AH1, as we said, This is between T infinity 1 and Ts1. This is the resistance. This is equal to Ts1 minus Ts2. Here the resistance is L by Ka. This is equal to Ts2 minus T infinity 2 divided by 1 by H2A. 1 by H2A. H2 is the heat transfer coefficient of this surface and H1 is the heat transfer coefficient of the left surface. H2 is the heat transfer coefficient on the right surface. So, in terms of overall temperature difference, if we want to write here the overall temperature difference, in terms of that, if we want to calculate heat transfer rate, then it will be T infinity 1 minus T infinity 2 and heat transfer rate is Qx. So it is T infinity 1 minus T infinity 2 divided by total resistance. And what is the total resistance? Total resistance is 1 by H1A plus L by Ka plus 1 by H2A. So we can write Qx equal to T infinity 1 minus T infinity 2 divided by total resistance, whereas total resistance is given by 1 by H1A plus 1 by Ka, thermal conductivity, Ka plus 1 by H2A. H2 is the film heat transfer coefficient of the right surface on the right side, film heat transfer coefficient. So now this is becoming the R total. Now composite walls may also be used, like if we have a composite wall, one component is identified by E, this is one material, another component is identified by F, another is G, and another is H, and these are bond together, but material wise they are different. They have different thermal conductivity and they also have different characteristics length or characteristics width, here L. And in this case the equivalent circuit between T1 and T2 will be, you can see T1 and T2. First resistance is this resistance, so this is given by LE divided by KE into A, and say this surface is at a temperature T1 prime and this is at a temperature T2 prime. So then resistance between them are in parallel. One is LF divided by KF into A by 2, another is LG divided by KG into A by 2. And between T2 prime and T2, the resistance is given by LH divided by KH by A. This is again the different material having thermal conductivity KH and characteristics length LH. So LH divided by KH into A. Here the effective area is again the total area, whereas for F and G effective area of heat transfer was A by 2. So this becomes the equivalent circuit. We can take yet another example. For example, this block here, this element is made of H1, thermal conductivity K1 and length is L1. This is L2 length and the effective transfer area is H2. Conductivity is K2. Here the effective transfer area. See, this is two-dimensional analysis. So basically area means H3 into the unit dimension which is perpendicular to the plane. So 1 into H3 is the effective heat transfer area and L3 is the length. And again This is the material is different. Here it is having thermal conductivity K4. This effective area is H4 into 1 and the length is, characteristics length is L4. So in the circuit between TS1 and T1 we have resistance given by L1 divided by K1 into H1. Between T2 and TS2 we have resistance, thermal resistance given by L4 divided by K4 into H4, and between T1 and T2 these resistances are in parallel. So this is given by, top one is given by L2 divided by K2 into H2, and the bottom part of the resistance is given by L3 divided by K3 into H3. So this is what is basically we can see in the derivation of the diffusion equation. We have done that, and then we have also discussed about boundary conditions, and we have solved simple one-dimensional problem. Simple one-dimensional problems. Also we have included the convective heat transfer surfaces, and found out the concept of thermal resistance. Now this governing equation can be extended in a similar way for two-dimensional and three-dimensional heat conduction cases. So we have studied generalized heat conduction case in all three dimensions, and we have solved one-dimensional problems from that. And as I said, that this can be extended to two-dimensional and three-dimensional heat conduction problems with the application of appropriate boundary conditions. Thank you very much. Thank you for your interest and your patience hearing. Thank you.